My name is Owen Haynes, and today I'll be presenting Physics 2212's Lab 2, Line of Charge. So in Lab 1, we created two charge tapes and then modeled their interaction as a point charge. However, in this lab, we aim to calculate a more accurate estimate for the charge of each tape by modeling them as a line of point charges. So the experimental setup was exactly the same as Lab 1. We used simple household materials to set up and perform the experiment, and then we're going to model those interactions using glow script. And ultimately, the result of this lab was that we found the charge of each tape to be 1.6801 times 10 to the minus 8 coulombs. The setup of Lab 2 was exactly the same as the setup of Lab 1. We placed a piece of tape on the table, we placed a piece of tape on top of that tape, and then ripped it up, and then, as you can see on the diagram on the right, the tape becomes charged. And then we create two of these charge tapes, we hang one, and then we bring another one up underneath the other one, and we see how far tape A, which is the bottom tape, pushes up tape B. After we made those observations and gathered that data, we need to actually do some calculations. So the fundamental physics principles used in this lab first are Coulomb's law, which on the left here is the force that one charged particle exerts on another charged particle based on the distance they are apart from each other. And then, because we're modeling, instead of just modeling the tapes as a point charge, instead of line of charges, there are going to be multiple electric fields created by those individual segmented point charges by dividing up the line of charge. So that means we need to use the superposition principle, which says that the total electric field is the sum of all the electric fields at that point. And then finally, we need to use Newton's second law to cancel out the force of gravity from the force of the electric field. Now we can set up our free body diagram. In this free body diagram, we are assuming that tape B is the system and the surroundings is tape A. On the right here, you can see that tape B is on the top, tape A is on the bottom. We have the force due to the electric field from tape A pushing up on tape B, and then the force due to gravity pushing down. And after everything comes to equilibrium, acceleration equals 0, so then we find that ultimately the force to the electric field equals the force to the gravity. So now we are making some assumptions. Air resistance is ignored. This is pretty reasonable because we're inside and there's not really any wind. We're in a very controlled environment. And then tape A and B are assumed to have the same charge. This is also pretty reasonable because they were made using the same process. So we're just making that assumption to simplify calculations. So now we set up the code. First we set up constants. So we have Coulomb's law constant and the constant due to gravity. We have our measured constants, which is the mass of the tape, and then this Q value, which is the charge of what we think each piece of tape is. Next we define functions. This top function, line 32 to 37, calculates the electric field at a certain point, and then this bottom function, 45 to 61, creates a line of charges, and this is the line of charges that we're going to use to represent our pieces of tape. And all that this function is doing is it's taking the total charge of the tape, and then it is dividing it into n segments. N is a value that you specify, and then it's giving each point charge Q divided by n charge. Now we're actually calculating the electric field and the electric force. So first we use that line charge function that we established last slide to create the top tape and the bottom tape, seen in line 76 and 77. Lines 106 to 121. We first use a nested for loop to calculate the total electric field at each segment of charge on the top tape exerted by the bottom tape. And then we simply multiply that electric field times our Q value, our charge, to find the force that A exerts on B. So after we calculated everything in the last couple of slides, this is just representing it visually, and you can see that the outcome of this is this. This is the result. I ultimately set my n value, which is the amount of point charges that the tapes are being split up into 20. So it's modeling it as 20 point charges interacting with each other. This green arrows here are the electric field, and then the white arrow is the total force from the electric field, and then the yellow arrow is the total force from gravity. As you can see, the force from gravity and the force from the electric field are equal, and we found that by guess and checking our Q value, and ultimately our Q value came out to be 1.6801 times 10 to the minus 8 coulombs. So sources of error in this experiment, when handling the tape, charge likely changed. If it brushed up against our hand or against some objects, electrons could have jumped to and from the tapes to alter the charge. And then also unaccounted forces in the surroundings and internal to the tape. In the model, we're assuming that tape A is kind of floating above tape B, but that's not true. It's being supported on either end by those erasers. And then also forces internal to the tape can kind of prop it up. So what if you had modeled each of your tapes as a single point charge like in the previous lab? So if we did that again, we would get the exact same result for our Q value as we did in lab 1. So in lab 1, we found our Q value to be 5.11 times 10 to the minus 9 coulombs, and in lab 2, we found our Q value to be 1.6801 times 10 to the minus 8 coulombs. So you can see that the Q2 value is quite a bit larger than the value that we found in lab 1, and exactly, to be specific, it's 3.288 times larger than Q1. So why do these estimates differ, and which value is more likely to be closer to the real value, and why? So these estimates differ quite significantly because we just use different models to calculate the charge. One was a point charge and one was a line of charges. Ultimately, the value created by this lab, lab 2, where the tape was represented as a line of charges, is likely to be more accurate because that's just more close to how the charges are actually arranged in the real world. In the tapes, the charges are not concentrated at a single point charge. Instead, it's distributed over the surface. So this isn't a perfect model, but having those charges arranged in a line is much more realistic to how it is in the real world.